As you can see from the title of this tutorial, this is all about electrons and light behaving as waves. We are coming off of a chapter where we learned all about the different parts of the atom and tried to get a rudimentary picture of what the atom looks like. And for the most part, we came up with a model that mirrors something along the lines of what we have up in class, right, in the corner, which is always here. And you can see that there are different parts to it. Right? We have the center of the atom here, which is filled with two different types of particles, which are our protons and our neutrons. And then along the outside, in some fashion, we have electrons, right, which you will learn are in different levels. So we're going to set that here. And in the meantime, right, we're going to draw that same picture. Right? Our picture of the atom to this point has a nucleus. And in the nucleus, we have protons, we have neutrons. And so if you remember, in the nucleus, we've got a lot of positively charged particles and neutrally charged particles. Then on the outside, we have electrons. And these were discovered by J.J. Thomson, and we decided that they were in something that was called the Electron Cloud. And the electrons are negatively charged, while the nucleus and the protons are positively charged. So, we have the foundations of what the atom looks like. The next question that had to be tackled was where exactly are the electrons in proportion to the nucleus? I know it's inside versus outside, but how far and in what manner are they oriented? So an interesting question arose among scientists once we had this picture of the atom. You have a positively charged center. You have negative electrons all around it. And the million-dollar question that scientists had to answer, because they know that opposites attract, was this. Why don't electrons crash into the nucleus? And that is the question that needs to be addressed. Two things that are going on here. First, electrons are attracted to the nucleus, one, because of size. Much like if we're looking at an Earth space lesson, the Earth is very, very massive and the Moon is significantly less. So Earth's gravitational pull pulls the Moon toward it and allows it to orbit. The same effect is happening here. Right? The nucleus is massive compared to electrons. So the electrons have a gravitational pull, so to speak, right, that pulls them to the nucleus. Now we'll call it something different. We'll call it the effective nuclear charge, right? But it's the same principle behind it. The second thing that has going is we have this opposite charge attraction. Negatives and positives always attract each other. So we need to figure out, why don't electrons crash into the nucleus? And that is where scientists tried to pick up once they found the different parts to the atom. The answer to the question is not incredibly simple, but we're going to tackle it in parts and make it very manageable. Like, the first thing you have to understand, if we're going to look at electrons and why they don't crash into the nucleus, is that there is a very clear relationship between electrons and light, or electrons in what we call the electromagnetic forms of a spectrum. And so we were in class, I would fire up some notes, and I'll do the same here so you can take a look at this. And the idea is that we want to get a little bit of background on how this is working. There is an important idea, right, that we want to relate electrons to light. Right? So the important idea is that light has certain properties. To this point, right, scientists believe that light behaved in two different ways. That it could behave as waves, and it could also behave as particles. The reason that is important has to do with some properties we know of light. Waves have the ability to go through things and bend around things. So for instance, the light that you're seeing from the overhead here, if I put my hand up, you see a giant shadow of my hand behind it because light does not have the ability to go through my hand. It does have the ability to diffract and reflect. It can go around it, it can bend, or it can shift as if we were seeing light going through water, how things are offset in the water because of properties. Those are ways light can behave as a wave. We'll tackle how it behaves as a particle a little bit later, but we're going to try to apply the same principles to electrons. So we are going to look at light as a wave. Light is one of the many forms of electromagnetic radiation. A little bit of a definition at you. Electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. Wave-like behavior being it moves like this, so to speak. Or with my PowerPoint pointer, like that. There are a lot of different types of electromagnetic radiation. Light is one of the many. Other ones that you may be familiar with: X-rays, radio waves, ultraviolet rays or UV, microwaves, infrared light or infrared rays. And all of these different types of electromagnetic radiation combine to form what we call the electromagnetic spectrum. So I'm going to slide a picture of the spectrum up, and we're going to talk about that. So as we look at the electromagnetic spectrum, you will see that there are many different parts to it. The particular part that this diagram has pulled out is the visible light spectrum, which is what you traditionally know as Roy-G-Biv, right? Red, orange, yellow, green, blue, indigo, violet. There is a relationship between the visible light spectrum and the electromagnetic spectrum. It is part of a larger thing. If we were to include the other forms that we were talking about, you'll find the visible spectrum lies somewhere close to the center. If we take a look at the spectrum, it compares two properties that we will discuss about waves: frequency and wavelength. Frequency is how often something happens. Wavelength is the distance between the waves. If you take a look, gamma rays, X-rays, UV rays are all above the visible light spectrum. Infrared, microwaves, radio waves, short wave rays, and long waves are all after it. These things have a unique relationship between each other, but what you will notice is that there is a direct relationship between the frequency of a wave and the energy of a wave. If I were to ask you which of these tend to be dangerous, you would probably say, we know that X-rays are not good for us. That's why they don't like to take them unless they have to. If you get a bunch of X-rays over and over again, it damages your skin. Gamma rays, which is nuclear radiation, is also very bad for you. We know UV can be bad. That's why they're always concerned about having you put on sunscreen or going to a tanning bed too much, because too much UV can damage your skin. Visible light now starts to get into we're not afraid of, right? The fact that I'm standing in front of this light and it's not melting my skin shows me that visible light is not particularly energetic. Right? So if you notice, X-rays have very high frequencies, they have very high energy. UV, high frequencies, high energy. As we go to infrared, microwaves, radio waves, right, TV waves, those we don't fear. We watch them all the time. They have a low frequency, which means low energy, and energy transfer to your skin or your body is what does damage. So let's talk about this idea of the relationship between frequency and wavelength and show you how to solve a few problems. Again, throwing a few definitions at you, like wavelength and frequency are two very different things. Like wavelength refers to the distance between corresponding points on adjacent waves. It varies depending on the form of electromagnetic radiation. So if we were to look at a wave, and I wanted to see its wavelength, what I do is I pick 2 points on adjacent, and if you know from math class, adjacent means next to each other, identical points on waves. So if I chose the top of this wave, and I went to the top of the next wave, this right here would be what we call the wavelength. Wavelength's abbreviation is a Greek symbol, lowercase lambda, which is like a Greek L. Right? That just means wavelength. So the lambda means wavelength. Frequency is a little bit different. The frequency is the number of waves that pass through a given point in a specific time, usually a second. They measure it in seconds. They give that value, 1/seconds, a name. They call it Hertz, named after a German chemist who did some research, right, or physicist rather, right, named Heinrich Hertz. Right? And many times, like you found out early on in the year, a way to honor scientists is by giving them units named after. So there is a relationship between the wavelength and the frequency, how often it happens. And what you'll find out is that they are inverse. As one goes up, the other goes down. That is why, as my frequencies decreased, my wavelengths increased. For instance, if this wave got longer, it would take more time for waves to pass through a certain point. So as the wavelength goes up, the frequency goes down. There's a really good website, right, that allows you to mess with wavelength and frequency. Right? If you go into Google, right, and type in wave on a string, right, wave on a string, click on the first site, and it will allow you to manipulate the wavelength and frequency of a wave to show you that as the wavelength shortens up, the wave compacts, it's more frequent. You see more peaks. As you stretch the wave out, right, the frequency of the peaks gets less, and it's less power. I want you to think of high energy things as waves that are really compact. It's like a closed fist versus an open hand. Right? The tighter those waves are, the more pack they have to their punch, so to speak. So, there is an equation that mathematically links wavelength to frequency. It is listed right here. Right? C equals lambda V, right? Which C is a constant. It is known as the speed of light. C is equal to 3.00 times 10 to the 8th meters per second. And what we found out is that frequency and wavelength of light will always lead to that constant. So anytime you see C, you always know what it is. It's 3.00 times 10 to the 8th meters per second. That's very fast. Right? The speed of light is very quick. It's 3 trillion meters per second. So, I want to show you how to solve some problems with this. Right? So we're going to turn the lights on. I have a few problems we'll look at so you can tackle these. First problem is right here. It says, what is the frequency of a wave that has a wavelength of 4.76 times 10 to the negative 9th meters. If I'm going to solve a problem like this, what I want to do is list the things that I know and list what I'm trying to find. So, as I read the question, things I always know tend to be numbers. So I know 4.76 times 10 to the 9th meters is something. As I look around, I can either recognize that wavelength is measured in meters, or I can see that it says has a wavelength of. So I'm going to label the 4.76 times 10 to the negative 9th meters as labeled. Once I'm done with numbers, I look at what the question is asking me to find. What is the frequency? Frequency gets a lowercase v. That's what I'm looking for. Next thing I do is I choose an equation that has these two things in it. And right now, we only have one. The equation is C equals lambda v. You're going to look at this and see that I have three things here, but I only have two listed here. Right? That's not a problem, though, because we always know what C is. C is the speed of light. It's 3.00 times 10 to the 8th meters per second. Once I get everything listed and I know what I'm trying to find, I want to rearrange my equation to solve for what I'm looking for. I'm looking for V. So to get V by itself, I have to get rid of lambda. So I'll divide both sides by the wavelength. Over here, those cancel, and I get that V is equal to C over lambda. From here, it's all about plugging in so long as my units match, a lot like my density problems from earlier in the year. Notice C has meters per second, wavelength has meters. Meters can cancel with each other, and my frequency is supposed to have seconds in it, so we're good to plug in. C is 3.00 times 10 to the 8th meters per second. Wavelength, 4.76 times 10 to the negative 9th meters. Starting with my units, meters on top and bottom will cancel. That leaves me with seconds in the bottom of the top, which is 1 over seconds. Remember, 1 over seconds is what we call a hertz. Now it's just a matter of doing the math. So you get your calculator out. 3.00 second E8 divided by 4.76 second E negative 9. My calculator says 6.3025 times 10 to the 16th. And lastly, we always take care of Sig Figs. 3 in the top, 3 in the bottom means I get 3 in my answer. So yes, 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 because it's a number bigger than 1, everything counts. So I drop the 2.5 because the 2 will not round the 0 up. And I get an answer of 6.30 times 10 to the 16th reciprocal seconds or hertz. Taking a look at another problem. It would say something along the lines of, what is the wavelength of a wave if it has a frequency of 6.21 times 10 to the 14th hertz? Again, attack this problem the same way. I have a number. The unit on that number is hertz. And you can either remember that hertz measures frequency, or you can see the word frequency right next to it. So V is equal to 6.21 times 10 to the 14th hertz. Then I look for what it's asking. Here's my question word. What is the wavelength? I'm looking for lambda. I'm out of numbers. I listed what I'm looking for. I choose an equation. Only one equation has these two things in it. C equals lambda V. Again, go back and list what C is. 3.00 times 10 to the 8th meters per second. This time, I need to get wavelength all by itself. So I'm getting rid of the frequency. So I'll divide both sides by V. That leaves me with lambda equals C over V. time the units are a little trickier. I see meters over seconds and I see hertz. But if you remember, hertz is equal to 1 over seconds. So hertz is able to cancel with seconds. So again, we can plug in 3.00 times 10 to the 8th meters per second over 6.21 times 10 to the 14th hertz. Hertz and seconds cancel, leaving my answer in meters. And now we just do the math. 3.00 second E8 divided by 6.21 second E14. And I get 4.8309 times 10 to the negative 7th. Okay? Again, I get 3 Sig Figs, so 4.830 will just be 4.83 times 10 to the negative 7. One thing to be aware of, do not get thrown off by the large negative, and in this problem that's covered, positive exponents. It is perfectly normal to get those types of numbers. So these are ways that waves and electrons, and light and electrons can behave as waves in some things that we can do. If you're still getting confused, please stop in for some help. And the next thing we'll talk about is how waves and light and electrons can behave as particles.